Hello, I'm Ed Close. Do you remember word problems? Well, the universe is the ultimate word problem that physicists try to solve using, among other things, something called the calculus, invented by Newton and Leibniz about 300 years ago. The problem with this is that the calculus of Newton and Leibniz assumes that the measure of things can approach zero infinitely closely. In the real world, however, of quanta, where everything is quantized, this is not true, and the calculus of distinctions corrects this error. Whether you know anything about the calculus of Newton and Leibniz or not, I'm going to ask you to put everything you think about it in the back of your mind for a little while I tell you about the calculus of distinctions. The calculus of distinctions incorporates the action of consciousness in observation and measurement. Application of the calculus defines fundamental processes at a level of logic prior to the development of other mathematical operations. A distinction, the basis of all observations, is a finite region distinguished within the field of consciousness by some property of dissimilarity from its surroundings. In other words, something that makes it stand out from everything else around it. The first distinction for any conscious being, you or me or anyone else, is the distinction of self from other. And the universe experienced by any conscious being is made up of the distinctions perceived by that being. A distinction is comprised of the relationship between three things: extent, content, and consciousness. And distinctions are represented symbolically as shown on this slide. The little curved line tells you that we're talking about a distinction. There's no other detail given at that point. If it has something under the curve, that indicates the content of that distinction, and the little n on the right-hand side represents the number of dimensions. So like if you're looking at something in a plane, then that would be 2. And it would be a circle or a line or a square or something on that plane or in that plane. If it's a three-dimensional object, then n would be 3, and a would be the content, whether it's matter, energy, or consciousness. Now, there's something called a theory of types that was developed by Bertrand Russell and Alfred North Whitehead, where they said there are 3 different types of statements. They can be true, false, or meaningless. And this would be true whether the statement is made in English or some other language or in mathematics, because mathematics is just a stripped-down version of a verbal statement. So true is represented by 1 in, say, in computer science, and false is represented by 0. So you have everything can be described in terms of 1 or 0. And the square root of -1 is considered the meaningless statement, or analogous to the meaningless statement in Russell's logic and theory of types. And in regular mathematics, it is called imaginary because it can't be plotted in 2 dimensions or 3 dimensions. Now, it's rather unfortunate that historically it was designated as imaginary, because the calculus of distinction reveals that the third type is self-referential. So let's look at the right-hand side here of distinctions. The curve just tells you there's a distinction. So if you have 2 statements that there is a distinction, it's still just that distinction. In the second one, which is across from false, we have a distinction within a distinction, or you can think of it as if the distinction were, for instance, a circle. If we move across the border into that circle, we are recognizing the distinction. If we move out again, then there's no distinction and you have a blank. So it's not the same as zero, but it just cancels out. Now the bottom equation represents the self-referential nature that so-called imaginary numbers have in the calculus of distinctions. And so it's, even though it equals the same thing as the one at the top, it's we would identify it in 3 dimensions. It's a meaningless statement because it says essentially that 0 or nothing or blank equals 1. And of course that's not true. But it's self-referential, and that's why when you see this in an equation, it turns out the same is true in mathematics of the normal type. When you see an imaginary number, it means you're talking about an extra dimension. It's an indication of an additional dimension. So Fermat's last theorem applied to the conveyance equation for the combination of 2 elementary particles in true units tells us that no 2 quarks can combine to form a third stable particle. But let's talk about true units for a minute. If everything is quantized, then everything is in terms of multiples of a small singular unit. That's what basically we're talking about right now when we mention true units. In the calculus of distinctions, we find that no 2 symmetric particles composed of true units can combine to form a third symmetrical particle. But in addition, we also find that if you have 3 symmetric particles that are identical, in other words, they have the same volume, like these 3 tennis balls, they can't combine to form a symmetric fourth particle. However, if you have 3 particles and they are of different size, different dimension, it turns out that they can be combined. And this is why you never see quarks in anything but combinations of 3. It's because they can combine and form stable spinning particles. Now all of the subatomic particles are spinning at very high rates of speed. Some of the angular velocities approach almost the speed of light. So you can see how they would be destructive and spin out of control if they're not symmetric. If they're, you could think of them as being lumpy or having some of the units sticking out, and they would wobble and throw themselves apart because they're being held together, attracted together by electric and magnetic forces. But with enough spinning and enough force, if they're not symmetric, they're going to fly apart and be unstable. Now, I promised to keep the math to a minimum, but some is necessary to explain the logic of true units, so please bear with me. And I'm using here conventional mathematical symbols because I think it will be understood better. When I learn something or discover something with the calculus of distinctions, it's always translatable into regular mathematics. It just reveals things that we don't find, we don't see in regular mathematics because we don't have consciousness involved. So the conveyance expression is a general expression, and for specific values of n and m, we have specific equations. So for example, when n and m are both equal to 3, this conveyance expression yields x1 cubed plus x2 cubed plus x3 cubed equals z cubed. Now the x1, x1, x2, and x3 and z all have to be integers if this is going to be the combination of the three elementary particles. So we have to have integer solutions and only integer solutions, but it turns out Fermat's theorem tells us that we can't combine two because if you have x1 cubed plus x2 cubed, it can never equal a z cubed. So that means that two, as we said before, that two particles, symmetric particles, cannot combine to form a third one, but three can. So solutions of this equation give us very handy descriptions of the combination of elementary particles. For example, if we think of them as spheres, now they can be any symmetric particle. They could be what are called regular polyhedrons. They could be cubes, they could be tetrahedrons, and so forth. And this would still work because as they spin, they will, spinning very fast, they'll look like spheres. The top equation here, you'll notice that the 4/3 pi, which 4/3 pi r cubed is the formula for the volume of a sphere. Now if it happens to be a sphere, this is what you would have. But notice that the 4/3 pi cancels out all the way across the equation. You can divide everything by 4/3 pi and get just r1 cubed plus r cubed 2 cubed plus r3 cubed equals r4 cubed. And this would be true for any shaped, any symmetrically shaped object. There'll be what I call a shape factor. If it's a cube, it would be 1 for each one of them. If it's a tetrahedron, it's another constant, but in every case it cancels out. So we find that there is the first simplest solution to this equation is 3 cubed plus 4 cubed equals 5, up to 3 cubed plus 4 cubed plus 5 cubed equals 6 cubed. Now this means that we can combine particles that have 3 true units, 4 and 5, and get one that has the linear measure of 6. So I know that's a little complicated, but it works out, and they're only specific. These are called Diophantine equations by mathematicians, and they're only specific solutions that are integer, and they happen to describe combinations of various elementary particles. So this becomes very useful when we've converted everything to quantized units, which we're calling true units. In the future videos, we'll explore how the calculus of distinctions in true units apply to atoms, elements, and all structures of the universe, including organic life. And I can tell you, amazing discoveries await, so stay with us.